Let us now consider the strength of a conjugate base. A strong acid ionizes completely in water. An example is the ionization of HCl in water to give hydrogen ion and chloride ion. Notice that a single arrow is used to denote the irreversible reaction, that is, a reaction that goes to completion. Alternatively, we can think of this as being a reversible reaction whose equilibrium position lies to the far right. The backward reaction occurs to a small extent, but it is so small that we can ignore the backward reaction altogether. This means that the chloride ion is a very weak conjugate base. Let's recall the meaning of a base. If we use the Bronsted definition of a base accepts H+, or going by the Arrhenius definition of a base in water produces hydroxide ions. A conjugate base means that it has one H+ fewer than the original acid. What does weak and weak conjugate base mean? It means to have a low or poor ability to serve as a base. A weak base, such as the chloride ion, therefore means that it is not quite able to accept H+ from water to generate hydroxide ions and HCl. The conjugate base of a strong acid has no measurable base strength. Link this to the use of the single arrow. Since HCl is a strong acid, it is 100% ionized in water. If the backward or reverse reaction were to occur appreciably, then HCl would not be 100% ionized in water. To maintain the idea that HCl is a strong acid, therefore, the backward reaction should not really occur, and chloride must necessarily have negligible ability to accept H+ to form HCl. A weak acid, unlike a strong acid, ionizes to a limited degree in water. An example is HF in water. Notice the use of the double arrow. This is therefore a reversible reaction. There is both a forward reaction and a backward reaction occurring all the time. Since HF is a weak acid, the forward reaction is not as favorable as the backward reaction. This implies that the product species H+ and F- have greater tendencies to recombine to return to being the reactant HF. Thus, the fluoride ion is a relatively strong conjugate base. Conjugate in conjugate base means that fluoride has one H+ fewer than the acid HF. Relatively strong base means to have a fairly good ability to accept H+ and generate hydroxide ions in water. As it does this, HF is formed. Note that if a species is a relatively strong conjugate base, it does not mean that it is a strong base per se. In fact, fluoride isn't a strong base as it is not able to totally accept H+ and totally revert to being HF. Let's focus on the word relatively. Whenever we use the word relatively, we are comparing one thing to another. Thus, relatively in relatively strong base means that its strength as a base is being compared to that of another base. But which base? It is the base on the other side of the equation. That is, it is water in this case. Though water is not explicitly written, it is there since the symbol Aq means aqueous and aqueous implies that water is present. Thus, fluoride ion is a stronger base than water. In all reversible Bronsted acid-base reactions, there is actually a competition that goes on between the bases on either side of the equation. The stronger base naturally wins as it has a greater ability to accept H+ than the weaker base. Similarly, two acids compete in such reversible reactions. One is a stronger acid than the other. They too lie on opposite sides of the equation. In this case, HF is the weaker acid while H+ is the stronger acid. Again, the stronger acid H+ wins the competition. Thus, the reaction that is favored is the one that forms the weaker acid and weaker base. A weaker acid and weaker base are less reactive and therefore more stable. The system favors the formation of more stable species, so in a reversible acid-base reaction, the stronger acid and stronger base react more readily to form the less reactive and more stable weaker acid and weaker base. In this case, it is the backward reaction that is favored. A strong acid has a weak conjugate base. A weak acid has a relatively strong conjugate base. But remember, this doesn't mean the conjugate base is a strong base. To qualify as a strong base, it has to be fully ionized. A relatively strong conjugate base doesn't satisfy this criterion. A strong base has a weak conjugate acid. A weak base has a relatively strong conjugate acid. Once again, being a relatively strong conjugate acid doesn't mean it is a strong acid. It isn't, since it isn't able to completely donate its H+. Rather, a relatively strong acid means that it is the stronger acid of the two competing acids in solution. A simple relationship between the ionization constant of a weak acid Ka and the ionization constant of a weak base Kb can be derived. For example, if we add the equation of the ionization of ethanoic acid to the equation of the ionization of its conjugate base, ethanoate, in water, then simplify by cancelling the identical species, ethanoic acid and ethanoate, we end up with water ionizing into hydrogen ion and hydroxide ion. Recall in the previous chapter that when two reversible equations are manipulated by being added, their equilibrium expressions have to be multiplied. So we write the Ka and Kb expressions, then multiply them. Simplifying, we get the product of hydrogen ion and hydroxide ion concentrations. This works out to be Kw, the water dissociation constant or the water ionization constant for the autoionization of water. Hence, Ka times Kb equals Kw.